Chapter 7 is over quantitative composition of compounds. Counting by weighing. If one orange has a mass of 186 grams, then 75 oranges have what mass? So if you know that you want the mass of 75 oranges and you know each orange is 186 grams, you put 186 grams on the top and one orange on the bottom to cancel out the oranges. So 75 times 186 gives you this answer right here. So you get 13950 grams or 13.95 kilograms. Technically, we would only keep 3 sig figs here, so we could also report this as 14.0 kilograms. Chemists will count atoms in a very similar way. We weigh our stuff. So because one atom weighs so little, we start using a bigger number called Avogadro's number. Avogadro's number is represented by 1 mole, which is 6.022 times 10 to the power 23. So every time I say there's 1 mole of something, I mean there's 6.022 times 10 to the power 23 things. We can use it for anything, like apples, eggs, anything. So for example, this is similar to 1 dozen, meaning 12. We just have a bigger number, and this number is called Avogadro's number. So like I said, 1 mole of atoms can mean 6.022 times 10 to the power 23 of atoms. 1 mole of molecules would mean 6.022 times 10 to the power 23 molecules. We can say the same thing about 1 mole of electrons, 6.022 times 10 to the power 23 electrons. Of course, we would use one regularly. We talk about a dozen of eggs. So if we were to say 1 mole of eggs, that means we just have a lot of eggs, which is 6.022 times 10 to the power 23 eggs. So we can use Avogadro's number or 1 mole as a conversion factor, remembering that 1 mole means there's Avogadro's number of that many items, whatever the object is. Sometimes the mole is on the top, objects on the top, mole on the bottom, objects on the top. Sometimes you have the opposite, where your mole will be on the top and objects will be on the bottom. It depends on our conversions. So how do we relate moles to masses? 1 mole of any element is defined as the amount of element that contains the same number of particles as 12 grams of 12 carbon, which in this case will be 6.022 times 10 to the power 23 atoms of 12 carbon. So this is carbon 12 here. And if we say 1 mole of carbon 12, we will have 6.022 times 10 to the power 23 atoms of carbon 12. So that's the official definition. 1 mole of any element can have the same number, which is 6.022 times 10 to the power 23 of atoms of any element, okay? But these elements, if they're 1 mole each, they can vary greatly in the mass, just because elements of atoms of different elements have different masses. For example, like we say, a dozen quarter versus a dozen dimes. Quarters and dimes will have different masses. So 1 mole of hydrogen will have a different mass than 1 mole of sodium, just because hydrogen weighs different. Hydrogen's mass is different than sodium's mass. And you can find these mass obviously from the periodic table. So we want to talk about molar mass. Molar mass is the mass of an element or a compound in grams that contain 6.022 times 10 to the power 23 number of the particles. So we usually express it to 4 sig figs. To determine molar mass, we take atomic mass unit from the periodic table and we add up everybody together. So for example, if we have Ca and F2, we take the mass of calcium from the periodic table, and then we take mass of fluorine from the periodic table, and we know we have 2 of them. So you take 40.08 grams plus 2 times 19.00 grams, and you get the molar mass of CaF2 to be 78.08 grams. So a lot of times I will symbolize molar mass as MW because I used to call it molecular weight. So that's something I just usually write. So keep that in mind. When I say MW, it really means molar mass. So here's a picture of some items that we have to show you the difference. So these are all 1 mole, okay? But because they all, from the periodic table, 1 mole of iodine weighs 126.9 grams, 1 mole of sulfur weighs 32.07 grams, 1 mole of iron weighs 55.85 grams, 1 mole of mercury weighs 200.6 grams. So they all look kind of different. I mean, you wouldn't be able to tell, but the point is 1 mole, everybody of all of them will have Avogadro's number of atoms right there. Okay, but each one of them have greatly different masses, and that depends on their mass on the periodic table. So let's try calculating. We want to convert moles of lead. How many moles of lead does 15.0 grams of lead represent? So Pb is lead, the old name is plumbum. So how would we do this? We would need to look up the grams and moles conversion factor, which means from the periodic table, you have 1 mole of lead is 207.2 grams of lead, or depending on which way we need, we might need 207.2 grams of lead on the top, 1 mole of lead on the bottom. So if you think about it, we are starting with 15 grams of lead, and we want to get moles of lead as our answer. So 15 grams should cancel out with grams on the bottom right here. So I would pick the first conversion factor to use. So let's show you that 15 grams of lead, 1 mole of lead, and then 207.2 grams of lead on the bottom. So we cross that off. So you take 15 grams times 1 mole divided by 207.2 grams. That will give us the answer in moles of lead over here. And our answer is 7.24 times 10 to the minus 2. We're keeping 3 sig figs here because there's 3 and there's 4, so we keep 3 sig figs. So here's another example. How many moles of mercury there's 23.0 grams of mercury represent? So you would need to look on the periodic table what the mass of mercury is. And this is what you'll see in the periodic table. Hg is 200.6 grams in 1 mole. So these are our 2 options that we can use. And we want to get from grams to convert it to moles. That means our grams needs to be on the bottom. So I would again pick this one right here where we do our math as 23.0 grams of mercury times 1 mole of mercury on the top, divide by 200.6 grams of mercury on the bottom. You cross off the mercury, and you can get 23.0 divided by 200.6. You get your answer is 1.15 times 10 to the minus 1 moles of mercury, or in the case we say B. So the next question is, how many atoms are contained? How many gold atoms? So gold is actually capital AU, are contained in 16.0 grams of AU. So this is gold. Gold's old name is aurum, AURUM, which is why the symbol for gold is AU. So if you look on a periodic table, you will see that 1 mole of gold is going to weigh 197.0 grams of gold. And of course, we know that 1 mole of gold always contains Avogadro's numbers atoms of gold. So we need to convert from grams, and then we can convert grams to moles. We cross off the grams, we get moles here. And then once we get moles, if they want the answer in atoms, we can use the fact that 1 mole of 1 mole of gold contains 6.022 times 10 to the power 23 atoms of gold. So that's how we're going to do it. So when we do 16 grams over here of gold, we convert it to moles first, where then now we cross off the grams. Our answer is in moles right now. And then we take the moles, we convert, we cancel the moles on the bottom off. we do 6.022 10 to the power 23 atoms on the top, and you get your answers in units of atom of gold. So when you do your math, it will be 16.0 grams divided by 197.0 grams times 6.022 times 10 to the power 23, and you can get your answer as 4.89 times 10 to the power 22 atoms of gold. Notice here we keep 3 sig figs because our number is 3 sig figs, 4 sig figs, and this is 4 sig figs, but we keep 3 sig figs right there. So the next question we have is how many titanium atoms are contained in 7.80 grams of titanium? So you'll need to look some information up from the periodic table. We need to convert from grams to moles and then to atoms, just like what we did earlier. And if you look on your periodic table, 1 mole of titanium is 47.87 grams of titanium. 1 mole of titanium also has Avogadro's number of atoms of titanium. Okay, so we do the same math again like earlier. We take 7.80 grams titanium times 1 mole titanium on the top, grams on the bottom, cancel out the grams. And then we take the moles and we cancel out the moles on the bottom here. And we take on the top, we have Avogadro's number, atoms of titanium. So your answer is going to come on atoms of titanium here. You take 7.80 divided by 47.87 times 6.022 times 10 to the power 23. You will get 9.81 times 10 to the power 22 atoms of titanium. Or in the case, our answer will be C. Next question. What is the mass of 2.13 times 10 to the power 18 atoms of lithium? So you'll have to look up the information about lithium. We need the molar mass of lithium, and then obviously we know Avogadro's number for lithium. 1 mole has 6.022 times 10 to the power 23 atoms. So right here, if you look on the periodic table, we get 1 mole of lithium is 6.941 grams. And 1 mole of lithium is 6.022 times 10 to the power 23 atoms of lithium. So we start with atoms, okay? We'll convert the atoms, cancel out the atoms to get moles. And then from moles, we'll cancel out the moles to turn it to grams. So that means this is a little bit different from earlier. We start off with atoms, so 2.13 10 to the power 18 atoms. We put the atoms on the bottom to get to moles. 1 mole lithium, 6.022 10 to the power 23 on the bottom. And then once your atoms are crossed off, now you have your answer in moles. The moles answer to convert to grams, you have to make sure your moles on the bottom so it gets canceled off, and times 6.941 grams lithium on the top. So when you do your math, it will be 2.13 times 10 to the power 18 divided by 6.022 times 10 to the power 23 times 6.941 grams, and you get your answer as 2.46 times 10 to the minus 5 grams of lithium. Again, we keep 3 sig figs in our answers because there's 3 sig figs here, 4 and 4, and we keep 3 sig figs. So over here, next question. What is the mass of 1.28 times 10 to the power 8 atoms of neon? So we'll have to look up periodic table information on a neon, and obviously Avogadro's number. 1 mole of neon is 20.18 grams of neon. So you'll start with atoms, cross off the atoms on the bottom, and get moles of neon. And the next thing is we want to cross off the neon, the moles of neon. So we'll use the opposite of this. The moles will be on the bottom, grams will be on the top, and then we can get our answer in grams. So 1.28 times 10 to the power 8 atoms neon times 1 mole neon divided by 6.022 times 10 to the power 23 atoms of neon times 20.18 grams neon divided by 1 mole neon. So we cross off the neons, moles of neons, atoms of neon. Your answer is in grams of neon. So you get 4.29 times 10 to the minus 15 grams of neon, or we say A. Next question. What is the mass of 1.05 grams of silver? So all you would have to do is get the molar mass of silver from the periodic table, which is 1 mole of silver is 107.9 grams of silver. Take the moles, You want to get grams, cancel the moles on the bottom, and your answer is in grams. So you take 1.05 times 107.9 grams divided by 1 mole. This cancels off. You get 113.3 grams of silver. How many sulfur atoms are in 2.27 moles of S8 molecules? Actually, I'm going to change this question. Instead of 2.27, let's just go ahead and do 1 mole. So let me cross that out. We'll do 1.00. Okay? Alright, so how many sulfur atoms are there in 1.00 moles of S8 molecule? What's important to remember is S8 molecule here is there's S and 8. So that means there's 8 sulfur atoms in one S8 molecule. And they're asking for sulfur atoms, so you gotta remember, first you convert from moles of sulfur 8 to number of molecules. Okay, you use Avogadro's number. And once you get the number of molecules of S8, then you will convert the fact that S8 has 8 sulfur atoms in it. So these are our two conversion units right here. 1 mole of S8 is 6.022 10 to the power 23 molecules S8. 1 molecule of S8 will have 8 atoms of sulfur. So we do 1 mole of S8, use Avogadro's number, cross off the moles of S8, and we get molecules of S8, and then know that 1 molecule of S8 has 8 atoms of sulfur. And that's how you will get the answer 4.82 times 10 to the power 24 atoms of S8, or in this case, C. Which statement is incorrect? 1 mole contains 6.02 times 10 to the power 23 molecules. Yeah, that's possible. That's correct. 1 molar mass equals mass of 1 mole. That's correct too. So the molar mass is for 1 mole. 1 mole equals 6.02 times 10 to the power 23 grams of a compound. That is not true because it just means object. It doesn't mean the mass. So C is wrong. Let's take a look at D. 1 mole of water contains the same number of molecules as 1 mole of carbon dioxide. That's true because each of them are 1 mole and both of them will have 6.022 times 10 to the power 23 molecules. One of them is water and the other one is carbon dioxide. So our answer is going to be C right here. That's incorrect. Let's talk about molar mass of compounds. Molar mass of compounds, we can use them for a lot of calculations. For example, if we want to do H2O, we would take, similar like earlier, 16 grams for oxygens, one of them, and 2 times 1.008, that's the mass of hydrogen, and you get the molar mass of water as 18.02 grams. We'll use these conversions a lot in our problems coming up. So let's find the molar mass of aluminum hydroxide, which is AlOH3. Okay, so we have 1 Al, 3 O's, and 3 H. Let's go ahead and find them out from the periodic table. Aluminum is 26.98, oxygen is 16.00, hydrogen is 1.008. So you add everybody up together. Don't forget to multiply by 3 and 3 for O and H because there's 3 of those. And you add them all up, you get 78 grams, or B. So we want to relate molar mass and Avogadro's number. We can say that if we talk about H2O, there's Avogadro's number of molecules, H2O molecules, and there'll be the same number of O, but double of the H atoms. Just because we know every time there's 1 water, there'll be 2 hydrogen and 1 oxygen. Okay? So that's how we got the masses here. So we gotta pay attention when the question asks for atoms or molecules or formula units. So if they say Cl2, Cl2 contains 2 moles of Cl atom, but only 1 mole of the Cl2 compound or molecule. So you have to pay attention. Are they asking for the Cl2 molecule, or are they asking for the individual Cl atom? How many moles are there? How many moles of NaCl are there in 253 grams of NaCl? So to do this question, we need to find the molar mass of NaCl. All you do is look them up from the periodic table, where Na is 22.99, Cl is 34.45. You add them together, NaCl will be 58.44 grams per each mole. So now that you know that 1 mole of NaCl has 58.44 grams of NaCl, we can use that conversion factor right here. And we take our grams and we put the grams on the bottom so it can cancel out and we can get our answer in moles. We will be keeping 3 sig figs, so our answer will be 4.33 moles of NaCl. Next question. How many moles of TiCl4 are there in 12.5 grams of titanium 4 chloride? So you would need to look up the molar mass of titanium and chloride, which is 1 titanium and 4 chlorine. So each chlorine was 35.45. 1 titanium is 47.87. And then there's 4 chlorine, 1 titanium. You get the molar mass as 189.7 grams of TiCl4. So then you take, if you know the fact that 1 mole contains 189.7 grams, you can use it to convert where you put the grams to cancel off on the bottom. So 12.5 grams to 1 mole TiCl4 on the top, 189.7 grams on the bottom. You cross off the grams, so you have your answer in moles, and you get 0.0659 moles of TiCl4 or A. Let's find the mass of 3.45 moles of Li2O. Li2O's name is lithium oxide. So lithium is going to be 6.941 and there's 2 of them, and each oxygen is 16.00. These are values from your periodic table. You add them up, molar mass is 29.88 grams for Li2O. So if you want the mass, all you do is you take the moles and then you make sure you cancel the moles on the bottom. So right there. And then you have your grams on the top. And you keep 3 sig figs in your answers because it's 3 sig figs and 4 sig figs. 3.45 times 29.88 will give you 103 grams of Li2O. What is the mass of 1.23 moles of pH3? So let's look for pH3's molar mass, where P is going to be 30.97 grams, H is 1.008, there's 3 of them, you add it up to get 33.99 pH3. Now, that's the molar mass, so if you need the moles, all you do is you make sure the moles cancel off on the bottom, and the grams will be on the top. So 1.23 times 33.99 will give you 41.8 grams of pH3, which will be this answer right there. How many molecules of H2S are present in 7.53 grams of H2S? How many atoms of H are present in the sample? So first you find the molecules, and then know that after you find the molecules that it's going to be double of the atoms right there. Because there's H2, that means there's 2 H every time there's 1 H2S. So let's go ahead and find the molar mass for H2S. H is going to be 1.008. S sulfur is going to be 32.07. You get your molar mass of 34.09 grams of H2S. And then you're going to use that where the grams should cancel off. So this value goes on the bottom, moles go on the top. Okay? And once you get the moles, you can use Avogadro's number to convert to molecules. And then remember, each molecule of H2S has 2 hydrogen atoms. So we do this right here. We have the grams of H2S, 7.53. We cancel off the grams of H2S with the molar mass, 34.09 on the bottom. And then we use Avogadro's number to get molecules of H2S. So this is the answer for the first part. which is 1.33 times 10 to the power 23 molecules of H2S. Okay, and the next part, I reminded you that every time you have one molecule of H2S, you have two atoms of H. So you want to cancel out the molecules here. So you take 1.33 times 10 to the power 23 times 2, and your answer will be 2.66 times 10 to the power 23 atoms of H. How many molecules of H2O2, which is hydrogen peroxide, are there in 0.759 of the compound? So first of all, you need to make sure you find the molar mass of H2O2, where hydrogen is going to be 1.008, and then oxygen is going to be 16, double of each one because it's H2 and O2. You get 34.02 grams of H2O2 for the molar mass. So if you have 0.759 grams of H2O2, you should cancel out H2O2 grams on the bottom where you get moles on the top. Once you get moles here, you can turn it into molecules by using Avogadro's number. You make sure grams is canceled out with grams on the bottom. You get your answer in moles, and we cancel out the moles on the bottom. We use Avogadro's number, and we get 1.34 times 10 to the power 22 molecules of H2O2. Again, when you do your math on a calculator, you do 0.759 divided by 34.02 times 6.022 times 10 to the power 23, and you get an answer of 366. Because your answer is limited by this 365, this is 4 and 4, so we'll end up keeping 1.34 times 10 to the power 22 molecules, which will give us this answer right here. Let's talk a little bit more about percent composition. Remember, percent means per 100 parts, and we're going to be talking a lot about mass percent of each element in a compound. Remember, percent composition is independent on sample size. A big sample size or a small sample size will still have the same ratio of percent composition. So we always pick convenient numbers, okay? Alright, so how can we determine percent composition? We need to know the compound's formula. So if we know the formula, we can use the molar mass to calculate the percents, or we can use experimental data. To calculate a percent composition, if we know the compound's formula, we will always assume, if you know the formula, we always assume we have 1 mole of the compound because it's a convenient number. Remember, percent composition, like we said earlier, it doesn't matter if you have a lot of stuff or little stuff, so we can pick whichever amount we want that's convenient. In our case here, if you know the formula, just assume you have 1 mole of that stuff. So you find the mass of the compound, which goes on the bottom, which we assume if it's 1 mole, we use the molar mass, and then you put whatever element, the mass of it that you're interested in. So like H2O2, you put the H part up here, like double of the H, and then H2O2 on the bottom here, and you just times 100 to get the mass percent. Let's calculate the percent composition of K2S. So we'll calculate percent composition of K and K2S and S and K2S. So what you want to do is find out, we assume, because we have the formula, we'll assume we have 1 mole of it. And remember, 1 mole of K2S, we'll find a molar mass of that, and it will have twice the K versus the sulfur. So 2 of 39.10, which is the mass of potassium right here, K, and then sulfur is 32.07. So the molar mass is 110.3 grams. This goes on the bottom. Now, if you want to find percent of potassium right here, you take 2 times 39.10 grams of potassium on the top, divided by 110.3 grams on the bottom, because this is a molar mass. We assume we have 1 mole because it's a convenient number, and then times 100, you get 70.90 potassium. So in this case here, if you wanted to find sulfur's number, you can actually take 100% minus 70.90, and you will get the answer for sulfur. Or you can do the same method. You take sulfur, 32.07 grams, divided by 110.3 grams on the bottom, times 100, you get 29.10 grams of percent of sulfur. So all the percentages must equal 100. So if you calculate the first one, you technically don't have to repeat the math here. You can take 100% minus 70.90 to get 29.10%. Find percent composition of H2O2. We want to find composition of O specifically in H2O2. So let's find the molar mass of H2O2 first, which is 2 times H and 2 times O. Then you get 2 times 1.008 plus 2 times 16.00 equals to 34.02 grams. So this is the mass of 1 mole of H2O2. That goes on the bottom. And then we want to find a percent composition of O. So you put the mass of O on the top, which is 2 times 16, and then you divide 34.02 times 100, you get mass percent of 94.06% oxygen, which is A. So to calculate percent composition of K2CrO4, we'll have to calculate for K and for Cr and for O. So what you want to do is first get the molar mass. So 2 times the mass of potassium, 39.10 grams, plus 52 grams for the mass of chromium, and 4 times 16 for the mass of oxygen, you get 194.2 grams as the molar mass. That will go on the bottom. And then to get percent composition of K, you take the K part, 2 times 39.10 grams of K divided by 194.2 grams, which is the molar mass. As remember, we're assuming we have 1 mole of this compound. So that gives us 40.27% of K. You do the same with Cr. You take the grams of Cr, which is chromium 52 grams, divided by 194.2 grams of the compound, times 100, you get 26.78% of chromium. To get oxygen's percentage, you technically could get 100% minus 40.27 minus 26.78. You would get the mass percent of oxygen. Or you can calculate using 4 times 16, same way, same formula. So 4 times 16 grams of oxygen divided by 194.2 grams times 100, you get 32.95% of oxygen. So on the other hand, if you were to calculate percent composition based on experimental data, we will need to get the mass of each component on the top, the element that you're interested in, divided by the compound mass, not the molar mass actually, just the mass. So let's erase this term off. Just the mass of the compound on the bottom, and then times 100. So here's the question. When heated in air, 1.63 grams of zinc reacts with 0.40 grams of oxygen to give an oxidized zinc compound. Calculate the percent composition of the compound formed. So to do that, you need to get the total of zinc and oxygen to go on the bottom, which is 1.63 grams plus 0.40 grams to go on the bottom. So that will give us 2.03 grams right here. And then you can take the part of oxygen, just 0.4 grams, divided by 2.03 times 100, you can get 19.7% of oxygen right there. Now, if you wanted to do the other component for zinc, we do the same way. We take 2.03 on the bottom, we take 1.63 grams of zinc on the top, times 100, we get 80.3% zinc. So technically, once you calculate oxygen or zinc, you can just take 100 minus the other part, you can get like 100 minus 19.7, you would get 80.3 anyway. So that's one way we can do that. Or you can do 2 separate steps like this. Aluminum chloride forms by the reaction of 13.43 grams of aluminum with 53.18 grams of chlorine. What is the percent composition of chlorine in the compound? So we're interested in the chlorine, so that means on the bottom we'll have 13.43 plus 53.18, and on the top we'll have 53.18, and then we multiply that term by 100. So right here, the total mass will be 66.61 grams because we add up the aluminum and chlorine parts. And then what that goes on the bottom, and we put the chlorine part on the top, times 100, we'll get a 79.8% mass percent of chlorine. So that will give us B. So the next thing we want to talk about is a little bit about empirical and molecular formula. Empirical formula is the smallest whole number ratio of atoms in a compound. So it's the simplest ratio, you can't simplify it further. Molecular formula tells you the actual formula of the compound, and it gives the accurate number, the actual number of atoms in one formula unit. And this is a whole number multiple of the empirical formula. So if the empirical formula was C and H, CH, the molecular formula could be C4H4, C6H6, C10H10, which is just a multiple of your empirical formula. So for example, they have C2H2 and C6H6. Both of them have the empirical formula CH. So here's the picture. There's benzene, C6H6, and C2H2. And then both of them have empirical formula of CH. This one is multiplied by 2. This benzene is multiplied by 6. Let's take a closer look. We have C2H2 and C6H6. They both have empirical formula CH. If you take a look, their percent composition, mass percent, is actually the same. However, obviously they're very different because they have different amounts of actual C and H. 2 and 2 versus 6 and 6. It'll give you very different chemical and physical properties. One cool thing though is you should note that they have the same percent composition. So molar mass, again, is the molar mass of the empirical unit, which is the CH value right here, and then whatever the multiplication number is. So like this would be 13.202 for the empirical, and C2H2 would be 2 times 13.02. C6H6 will be 6 times 13.02. Now, if we want to calculate empirical formulas, here's our general strategy. First thing you want to do is, if you are given mass percentages, we assume we have 100 gram. So mass percent doesn't depend on how much you have. So a lot of stuff or little stuff, the ratio stays the same. So we always pick a convenient number. So right now, if we want to pick a convenient number, it would be, if we're talking percentage, we always assume 100 gram, because then we can say if it's 65% carbon, we assume the whole 100% is 100 grams. Therefore, 65% carbon will be 65 grams of carbon. It will make our math a lot easier. And then once you have grams, sometimes they provide grams right away. If you already have grams right away, you can just go straight to step 2. If they give you mass percent, assume it's 100% for 100 grams, and then you get your grams. Once you get the grams, you convert to moles using molar mass, and then these numbers usually are not whole numbers. They're going to have a lot of numbers behind it, so try to follow the sig-fig rules there. And then you divide all the element units by the smallest mole amount. So it will make more sense when we see some examples. We divide it by the smallest, so that way you can get a ratio. So sometimes after you divide, you still have fractions. You will multiply by a common factor to make sure you get whole numbers, because empirical formula, well, it needs to have whole numbers, so you can't keep anything that has fractions in it. So here's an example. The example is to calculate the empirical formula for a compound that contains 11.19% hydrogen and 88.79% oxygen. So since they gave us percentage, we want to assume now we have 100 grams for 100%. So that means we have 11.19 grams of H and 88.7 grams of O. And then we'll take each one, use the molar mass, and we'll change it to moles of each compound. So I have 11.10H, and then I have 5.549 moles of O. Okay, so that's just saying first we turn it to grams, and then we use the molar mass to convert it to moles for both of them. And then now we have H as 11.1, O as 5.549. So obviously the smaller number is 5.549. We'll divide both of them by 5.549. So this will be 1 for oxygen H would be 2. So you can see now the ratio is 1 oxygen to 2 hydrogen. So our formula is 1 oxygen, 2 hydrogen, so H2O. And that's our empirical formula. Next question, calculate an empirical formula for a compound that contains 56.68% potassium, 8.68% carbon, 34.73% oxygen. First of all, let's assume 100% is 100 grams, then each of these numbers are going to be converted to grams. And that's what we'll do first. So now that we know we have 56.68 grams of potassium, 8.68 grams of carbon, 34.73 grams of oxygen, we'll then convert everybody to moles. So we have moles of potassium, moles of carbon, moles of oxygen. Carbon is the smallest number, we'll divide by carbon, so everybody will be divided by 0.723. So obviously, if carbon is divided by the same number, the ratio for carbon will be 1. And if you do it for potassium, you end up getting 2. For oxygen, you end up getting 3. So your formula is actually 2 Ks, 1 carbon, 3 oxygen. So our formula would be K2CO3. So our answer, if we had an answer, it should be C, which goes, let's add a 2 right there. It's K2CO3. Alright, calculate the empirical formula for a compound that contains 2.233 grams iron and 1.926 grams of sulfur. So the first thing we want to do is we already have grams, so let's go ahead and convert them to moles. Okay, so usually if they give us a percent, we convert to grams first and then do the moles, but since they gave it to us in grams, let's go ahead and turn them into moles. So you do that, you have irons, you have 0.03998 moles of iron. We keep 4 sig figs here, so these are 4 sig figs. You see, because there's 4 sig figs and 4 sig figs here. Now, and then we do the same. We want to get the moles of sulfur. Moles of sulfur is 1.926 grams of sulfur times 1 mole of sulfur divided by 32.07 grams of sulfur. You get 0.06006 moles of sulfur. So now that we have moles of sulfur, the smaller number is the iron, which is 3998. We'll divide both of these values by 0.3998. So what you'll get is 0.3998, 0.3998, you get 1. And then you get 0.6006, 0.3998, you get 1.5. So this is when we start saying, well, usually we stop here and we can get a whole number, but in this case, you see how it's still a 1.5. We can't write Fe and an S 1.5. So what we have to do is multiply both by 2 to get rid of the fraction right here, and we get whole numbers. We get 2 and then we get 3. Okay, so you got to remember, if after you divide by the smallest number, if you have a fraction, still a number here, decimals, what you want to do is get rid of it by multiplying with a number that turns both of them to whole numbers. So what we get here is Fe2S3 instead of Fe1 or Fe and then S 1.5. Okay, so we get Fe2S3 or D. So just in case you weren't too sure about fractions and what number to multiply, here's a guide for you. If you have 0.2, you multiply by 5, 0.25, you multiply by 4, 0.33. So whatever the number, this can't be 0. It's like maybe it's whatever it ends with. If it's 0.33, you times 3. Like if it's 1.4, you end up multiplying by 5. That's the way we can get rid of these fractions right here. So here's a table for you to refer to in case you weren't too sure what number you can use. So the next thing is, if you know the molar mass, you can actually calculate molecular formula once you get empirical formula. So we've been calculating empirical formula before this, but we can also find molecular formula if we know the empirical formula and molar mass. So because molecular formula is a multiple of empirical formula, once you find the empirical formula, all you do is you get the mass of the empirical formula, and then you take the molar mass divided by the mass of empirical, and you get a multiple, a ratio there. So then you take the ratio and you multiply with the empirical formula. So that's the value of n, that's the ratio that we're talking about. So you take the molar mass divided by empirical mass, you get the n factor there, and then your empirical formula will be multiplied with the n factor to get the molecular formula. So sometimes your empirical formula is the same as the molecular formula, if you notice. Sometimes that happens. See, like this one, CH2O is CH2O. So sometimes when a molecule is really simple, the empirical and molecular is the same thing. Here's some more examples of empirical formula and molecular formula. A compound with empirical formula NH2 was found to have a molar mass of 32.05. What is the molecular formula? So this question is pretty simple because they already gave you the empirical formula and the molar mass. All you have to do is find the molecular formula. Now there are questions that will give you information like mass percents, and then they'll give you a molar mass and ask you for the molecular formula. So you'd have to go through the whole steps of finding empirical formula first to get to this part before you can get the molecular formula. Okay, so let's just, we'll skip all that part since we already have our empirical formula. NH2, let's find the mass of NH2. And then we can take 32.05 divided by NH2's mass, and we can get the multiple ratio that we will need to use. So our n factor there. So 32.05 is the molar mass, and empirical mass will be N 14.01 plus 2 times 1.008 for H, and you get your multiplication ratio of 2. So once you know it's 2, you just know that your molecular formula will be the empirical formula times 2, which will give you N2H4. That should be an H right there. A compound with an empirical formula NO2 was found to have a molar mass of 92. What is the molecular formula? So let's find the empirical mass of NO2. And that's going to be right here, 14.01 plus 2 times 16. And then you have 92 as the molar mass on the top. Okay? So 92 with the molar mass divided by the empirical mass, you end up getting a factor of 2. So that means your molecular formula will be NO2 times 2, which is N2O4. In this case, the answer B. Next question. Propylene contains 14.3% H and 85.7% carbon. It has a molar mass of 42.08 grams. What is its molecular formula? So this is the question where you have to first solve for the empirical formula, find the empirical mass, and then take the molar mass to divide by the empirical mass. Then you can get the multiplication ratio for the molecular formula. So let's go ahead and start. 14.3% H will become 14.3 grams of H. And this will be 85.7 grams of carbon. And then we'll take both of them, turn them into moles. So now we have moles of hydrogen and moles of carbon. And then carbon has a smaller number, 7.14. So we divide both of them by 7.14. So your ratios here is going to be 7.14 divided by 7.14, so you get 1 for carbon. And then for H, you get 14.2 divided by 7.14, you get 1.99, which is just rounded to 2. So it's C and then H2. So now we have to find the CH2's mass. Put it on the bottom. 12.01 for C, 2 times H, 1.008. And then you put the molar mass on the top, remember? Molar mass divided by the empirical mass will give you the factor, in this case 3. So we need to take CH2 times 3 to get our new molecular formula, which will then give us the answer of C3H6. Here's another question. Calculate the molecular formula for a compound that contains 80.0% carbon and 20.0% H with a molar mass of 30 grams. So same thing, just an extra practice here. First step, convert to grams, and then change both of them to moles. Once you have the moles, you divide by the smallest number, and then hopefully you find an empirical formula that way. Sometimes you have to multiply with multiplication to get rid of the decimals, and then we'll use the molar mass to find the multiplication factor. So in this case here, 100 grams, so 20 grams of H, 80 grams of carbon, and then we convert both of them to moles, and carbon's number is smaller, so we'll divide both of them by carbon's number, and you can see here carbon is going to be 1, and the ratio for H will be 3. So it'll be H3 and then C, so it's CH3 for my empirical formula. So then you need to put the empirical formula number on the bottom, C and then 3 H's on the bottom, and 30 grams the molar mass on the top. Our multiplication factor here is 2, so that means our answer will be CH3 times 2, so it's C2H6. Our answer is C right there. Alright, here's a couple more questions. In which pair would both compounds have the same empirical formula? So H2O and H2O2 are two different empirical formulas. Well, this one is molecular formula and the empirical, but H2O2 will be simplified to just HO, so they're different. BaSO4 and BaSO3 are also different because they cannot be simplified further, so they're both different empirical formulas. FeO and Fe2O3 are different empirical formulas. C6H12O6 has empirical formula of CH2O. So this one is C2 and an H, there's 4 of them, and O2, so this one will be CH2O, which is the same as CH2O, so D would be my answer right there. Now, for the next question, so let's pick D for the answer. And then for the next question, 4.5 grams of nitrogen for every 7.71 grams of oxygen, and it has the same empirical and molecular formula. Well, that's nice. So when you get the empirical, it is the same as molecular. Identify the compound. So N is 14.01 grams per mole, O is 16 grams per mole. So we'll have to do this here. First of all, we take grams of each one. Let's turn it to moles. So what we want to do is take 4.50 grams of nitrogen, and we'll turn it to moles, where 1 mole of nitrogen is going to be 14.01 grams. This will give us moles of nitrogen, and I'm going to get 0.321 moles of N. We'll do the same for oxygen. So we take 7.71 grams of oxygen, and then we get it to moles. 1 mole of O is 16 grams, and then we get 0.482 moles of O. So you see how N is the smallest number? So what I like to do to let you guys visualize this is write this down here. N is 0.321 mole ratio. O is 0.482 mole ratio. So that's how we know, like, well, that looks silly because it's all decimals. We have to turn it into whole numbers, so that's why we divide by the smallest. So divide both of them by 0.321. Okay, so obviously now that becomes 1, and this one actually turns out to be 1.5. Now remember, earlier we had a case like this where I had a fraction. You can't still write N and an O 1.5. That doesn't work. So what we do is we take this whole thing and multiply it by 2. So we get N2O3 as our answer, which then would be C.